You're watching a Channel 98 NBISD TV production.
Hi, welcome to another episode of That Geometry Show. As always, I'm your host, Kevin Corpy, and today's lesson is all about surface area. We kind of did a little bit with surface area last week, but today we're going to be looking at surface area of some very special or very specific solids, and they have very specific formulas too that we need to get used to using. A lot of this is going to be on the standardized test come April, and they typically give students a lot of problems. So pay very special attention today. Take good notes. You can remember you can get those handouts from the district website, and hopefully you'll learn something. Okay? Hope you stick around and learn something and learn something. Let's learn. All right, lesson 24. This is going to go along with your textbook 3.1 and 11.3 and 11.4. All right, today surface area prisms, cylinders, pyramids, and cones. Now, at the end of the last episode, we did look at lateral surface area of a cylinder. Remember the pineapple juice? Well, today we're going to explore the surface areas of some other special 3D solids. And being so special, naturally, they have special names and special area formulas that we're going to be using. Now, these area formulas you don't necessarily have to memorize. Whether you're in class or on the standardized test, you're going to be giving a formula chart, possibly. Ask your teacher about the test. But definitely on the standardized test, the TAKS, you're going to be given a chart. And you have to know how to read it. This is the one from previous years. And starting this year, there's actually going to be a new chart. So basically we have area formulas. We have rectangle, triangle, trapezoid, circle, and a lot of surface area formulas, cube, cylinder, lateral, cone, and sphere. But the new chart will look something like this. It has a much larger area for the formulas that deal with area and surface area. How about that? And we have some new letters that we have to deal with. So fear not, we're going to get you used to these equations because we're going to be using the new ones that are on the new TAKS test today, on today's show. So remember that a prism from previous episode on polyhedron is nothing more than a polyhedron with two congruent bases, and they're in parallel planes. They have uniform cross sections, so here are some examples. These happen to be right prisms. This is a pentagon, and it has a partner in the back here that's also a pentagon. Those are the two congruent bases. We'll label that as a base. And then the other faces that wrap around the pentagon, joining the corresponding sides, are called the lateral faces. And they're parallelograms. So remember, we named the prism by the shape of the polygon that is the base. So this would be a pentagonal prism. This would be a triangular prism. Again, a triangular regular prism, because the faces or the bases in this case are congruent, and the hexagonal or hexagonal prism, because we have two bases that are hexagons. So again, just to kind of go over the anatomy of it, we have the base, which in this case would be a triangle, and the other base would be another triangle, and the sides that join it are called the lateral faces. Where two lateral faces come together, we have something called a lateral edge. So in this pentagonal prism, we have 1, 2, 3, and then two more we can't see, 4, 5 lateral edges. And they're congruent. And then these faces are also congruent, and they're parallelograms. Okay? Well, the ones that we've been looking at have been regular prisms because the faces or the bases were congruent. But we also have to classify them by whether they're right or oblique. What is that, you said? A right prism is basically a prism whose height is the altitude, and it's perpendicular to the base. So look at this cube right here, which is a rectangular prism. The height, since it's perpendicular to the base, this becomes a right prism. And if you look at this one here, this is a triangular prism, and it could be regular, but because the bases are congruent, but this is like something that was poorly built. You know, it's kind of fallen over, it's leaning a little bit. We'd have to drop an exterior altitude to make it perpendicular, and that would be the height. Okay, so it's kind of leaning over. We call those oblique. Oblique just means slanted. Now we can find the surface area of these prisms as we did before, but we can also derive the formula that's going to be on that chart, which makes it much easier to use and makes the calculations much faster. So here we go. The lateral surface area of a right prism, and we're going to use the letter L for lateral surface area, makes sense. It's the product of the perimeter P, perimeter is going to be P, of the base times the altitude or the height, which we're going to call H. So we can translate that into a formula and call it L equals PH. Now, you might have been learning in class or on a previous episode. Let's look at this triangular prism. We said that if we just added up the areas of each, in this case the three lateral faces, we could add those up and get the lateral surface area. Well, let's call the length of one side of the base S, and this being H. Well, notice that since S times H gives me the area of that lateral face, I have SH plus the two sides we can't see are also going to have S, if this is an equilateral triangle, times H. So that's another S times H, plus another S times H, the third side. So by deriving the formula, what we can do is we can pull out the H. We can factor it out. And by doing that, we're left with S plus S plus S. Well, what is S plus S plus S? It's the sum of all three sides. Well, that, by definition, is the perimeter of something. You add up all the sides. So we end up with S plus S plus S, or P times the height, which gives us our H. So that's the derivation. That's the only one I have time to derive on today's lesson, but it gives you an idea that these formulas, although they might look different, they really accomplish the same thing. Now, to get the entire surface area, or the total surface area, we need to simply add the two congruent bases. So lateral is just the side, add the two congruent bases, and we're going to use the letter B, capital B, to represent the area of one of the bases. So I'm going to use SA for total surface area, and we get this equation. The total surface area then is PH, which is the lateral, the sides, plus 2 times the base area, big B. And don't forget to double them because we have two bases, and big B is just the area of one of the bases. Now this is very important. Be sure to read your questions very, 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 did I say very, very carefully to be sure that you're finding the correct quantity. If it says find the lateral surface area, of course you have to find the lateral. If it just says to find the surface area, it's implied to be the total. So lateral has to be specifically stated, otherwise it's total. Sometimes you might be asked to find both of them. It's two different formulas, it's two different quantities. Be careful. Let's look at an example. We want to find the lateral and the total surface area for this triangular prism. So notice that it is a regular prism because the base is an equilateral triangle. So let's go ahead and look how we're going to find the, let's do the lateral surface area first. Remember, the lateral surface area is the perimeter, P, times the height. Well, 6 is labeled to be this side. That's going to be H. And the perimeter of the base. Well, I know that one of the sides is 4, but because it's equilateral, they're all equal to 4. So let's go ahead and plug in. The perimeter is just 4 plus 4 plus 4, or 4 times 3, times the height, which is 6. Well, 4 times 3, or 4 plus 4 plus 4, is going to be 12 times 6, and 6 times 12 is 72. Now, notice that the units are given. We want to include units. We're basically doing perimeter, which is in inches, and 6, which is in inches. So we're multiplying inches times inches, so this would be in square inches. So we can say that the lateral surface area is 72 square inches. Well, now we need to work on the area of the base, which is B. Let's work on B, and then we'll just combine our results. Now, B is a triangle. Let's use this one down here. Remember, the area of a triangle, is 1/2 the base times the height. Okay, well, because this is equilateral, if I drop a perpendicular or an altitude to obtain the height, it also becomes a perpendicular bisector. So I can create a right triangle whose side length right here is going to be half this length. If the whole thing is 4, this becomes 2. Well, I know that this side length, which ends up being hypotenuse, is one of the side lengths of the bases, which is 4. And this right here is H, which is what I'm looking for. So I can use the Pythagorean theorem before I actually get to the base. So let's go ahead and find H by the Pythagorean theorem. I get H squared plus 2 squared, those are the two shorter sides, equals 4 squared. And now I'm going to take the liberty of skipping a few steps, just for the sake of time, and showing that H is equal to the square root of 16 minus 4, which is 12. And simplifying radicals is another thing entirely. The square root of 12 is the same as the square root of 4 times 3, but 4 is a perfect square. So we can call that 2 square root of 3, and that's in inches. Now I get a decimal approximation of that. It's about 3.164, but I'm going to go ahead and use the exact answer in the calculation so I don't have rounding error. All right, so now that I know the height of the triangle, I can find the area of the base. The base is going to be the area of the base, sorry, is 1/2 the base of the triangle, which is the whole thing all the way across, which is 4, times the height, which is 2 square root of 3. Now I just got to simplify. Well, half of 4 is 2. 2 times 2 is 4. So I get 4 square root of 3 inches squared. And again, if you want to know what that is approximately, you can go to the calculator and figure it out. What I'm going to do is I'm going to actually add it together now. So we have the total surface area, SA, is the sum of the lateral, which is 72, plus the base doubled. Remember, we have one up top, one at the bottom, top and bottom. There we go. And we just found the area of one of them is that. So it'll be 2 times 4 square root of 3. And if we add those together, we get 72 plus 8 square root of 3. Okay, if you have a calculator, you can punch that in and see what the answer comes out to be. All right, let's look at another one. The cylinder is another type of solid. Now, it's not a polyhedron. Do you remember why? It's because the face or the base is circular, and a circle is not a polygon because it has a curved surface. All right? But you can think of a cylinder as a prism that has circular bases. They have uniform cross sections. We also have oblique cylinders. So think of again of a cylinder that has been poorly built, like a slinky maybe that you can push over to the side. It's slanted. We're going to be looking at these right cylinders, okay? So we have a circular base with the radius of that circle being r, and we have a height which forms perpendicular to the base of h, all right? We can talk then about the lateral surface area of that cylinder. Here's a net of the cylinder. And we did this on the previous episode. If you unroll the sides, you get a rectangle. And the height is just the height of the cylinder. But the width of the rectangle is nothing more than the circumference of the circle. Well, the circumference of a circle has a formula of 2 pi times r. So length times width is nothing more than 2 pi r times h. And that's where this formula comes from. Now the area of the circle, which is the base, to get the total we need to add the area of the bases. So that area plus that area, well those are circles, so the area of a circle, and this is again on a formula chart, it's pi r squared. So we can combine the lateral plus 2 times the area of the base to get this. The surface area of a cylinder, of a right circular cylinder, is 2 pi rh, that's the lateral, plus 2 times pi r squared, which is twice the area of the base. Now, there's another version of the formula. We have a common factor of 2 pi r that we can pull out, and we get this other formula. They're both on the tax formula chart. Depending on the circumstances, one might be easier to use. I'm going to go ahead and use the first one because I'm going to do the lateral and the base area as 2 separate calculations, and then I'll just combine them together. So here's our example. Find the surface area of the green, notice it's green, right, which means that it forms a perpendicular to the bottom, circular, the bases are circular, cylinder. Man, it's a lot of adjectives describing that thing, but they're all important. Okay, now the H I can label as 15. That can be this right here. And D, well, what is D? D is the diameter. And the diameter is the distance all the way across the circle. The radius is only half of that length, or half the diameter. And our equation up here uses the radius. So you have to be careful when you're given quantities. You can't just jump in and start plugging any old number into any old part of any old equation. We need to find the radius first. So let's go ahead and do that. The radius is basically the diameter divided by 2. So if the diameter is 10, the radius is going to be 5. Oops, getting ahead of myself here. Let's try that one more time. 10 divided by 2 is 5 feet. Okay? Now that I have that, I can go ahead and find the total surface area. Well, let me find the lateral surface area, and then I'll add it to the total. We can actually just do that by using this formula. So the surface area is going to be 2 times pi, and remember pi is just approximately 3.14. That's also going to be given. It's pretty easy to memorize. 2 times pi times the radius, which we just found to be 5, times the height, which is 15. That's lateral, plus 2 times the area of the base. Well, the area of the base is pi times the radius, which is 5, squared. My goodness, these are a lot of calculations. What do we get when we do all that? Well, I'll let you do it at home. You end up with 150 pi, that's keeping it as an exact answer, square feet, which comes out to be approximately 471. Oops, I'm getting ahead of myself again here. This is 150 square feet plus 25 times 250 pi square feet. So you can go ahead and add those together. I didn't bring my calculator with me today, but these are exact answers. Now, I can go one step further here. Since they're both have pi in them, I can get 200 pi square feet. It's going to be a little more than 600 square feet. Okay? Pi times 200. All right, don't go away. It's time for that break. We'll be right back. I hope you come back with us.
Some of my friends smoke weed and I don't. It's whatever. I drive the car so they won't have to get behind the wheel. I pick where we eat so they won't have to worry about choosing a place. I tell them when we heading out to the party so they won't have to worry about being on top of time or anything like that. And at the party, I'm the one talking to all the ladies. And my boys just sit there till it's time to go and I'm like, hey, get back in the car, man. But basically, they don't have to worry about living life. I live it for them. Until I go to college, then y'all somebody else's problem. But until then, it's whatever.
All right, welcome back to That Geometry Show. Today's episode, we're talking about prisms, cylinders, pyramids, and cones. So let's get right back to the math. All right, on to pyramids. Pyramids are three-dimensional closed surfaces. The one base of the pyramid is a polygon, and the lateral faces are always triangles with a common vertex. Remember, we classify these by the type of polygon the base is. So we have triangular pyramids, square pyramids, pentagonal pyramids. The vertex, or the point of the apex of the pyramid, is not in the same plane as the base. Okay? The pyramids are also, they are called polyhedra because their faces are triangles, which are polygons. They're not curved. Now, the common pyramids are regular pyramids, which means that the base is congruent. And the regular pyramid has a regular polygon for a base, and its height meets the base at its center. So the height would be dropping right down and meeting right here in the center of that square base. We'll call that C. The slant height, that's a new thing. The slant height is the altitude of each lateral face. So look at this triangle here that's kind of tilted backwards. If I draw the height or the altitude along the diagonal so that I get the altitude of the face, this is what we're calling the slant height. And a typical letter used for that is a script letter, lowercase l. All right, now in a regular pyramid, the lateral edges, which are these, where the triangles are joined, are congruent. And since the base is a regular polygon whose sides are all congruent, we know that all the lateral faces are isosceles triangle. That's pretty nice to know. That's going to be congruent to that all the way around. Now the lateral surface area, L again, of a regular pyramid with a base perimeter of P and a slant height of, there's that script letter L, is given by L equals 1/2 the perimeter length times the slant height. And again, this comes from the perimeter being the base, the sum of the bases all the way around. Okay? To get the total surface area, again, we just need to add the area of the base. So the lateral is going to be all the triangles around the side. To add the base, it's just going to be whatever the area of that specific polygon is. We only have one base, so we don't have to double it in this case. All right? Let's look at an example. We want to find the lateral and the total surface areas of the following pyramid. So what are we given? We're given S. This is actually, I'm sorry, this should be L. That's a slant height. Some people use S for slant. Most of the formulas you can see use L. We have this length of the base, which appears to be a regular pentagon, is 8. And we're also given that the apothem of the base is 5.5. We'll get to that in a minute. So let's go ahead and find the lateral surface area. The lateral surface area is 1/2 the perimeter. Well, notice the perimeter of the base is going to be a pentagon whose lengths are 5. So that's going to be 8 times 5. That's going to be the perimeter, times the slant height, which is given to be 15. All right? So I can do the calculations. That is going to come out to be, let's see, 40. Half of that is 20. 20 times 15 gives me 300, and the units are centimeters squared. Now we want to find the total surface area. Let's go ahead and find the area of the base first. This is going to require a little bit of work. It's going to be a regular pentagon. Remember, the formula from a previous episode is 1/2 of the perimeter times the apothem. 1/2 of Pa, 1/2 of your dad. Remember that? Okay, so we need to know the apothem. Well, it's given to be 5.5, thank goodness. If we weren't given the apothem, you'd have to use a little bit of trigonometry to find it, and we haven't had that lesson yet. So now we can go ahead and find the area of the base. It's going to be 1/2 the perimeter, which again is 8 times 5, or 40, times the apothem, which is 5.5. And if we calculate that, we get, let's see here, 110, calculator will help you do this, centimeters squared. So now the total surface area, SA, is going to be the lateral, 300 centimeters squared, plus the area of the base, one base, we don't have to double it, 110 centimeters squared. And that's a pretty easy one to do without the calculator, so avoid the temptation. 410 square centimeters. So we got lateral, which is 300, and total, which is 410. We add the base and the lateral together. On to cones. We've talked about cones before on the say what portion when we looked at the conic sections. We're going to look at lateral surface area today. Now just to review, a cone is a three-dimensional closed surface. And when we talk about a cone, we're talking about a right circular cone, so that, again, the height is perpendicular to the base. The base is going to end up being a circle, and this is not a polyhedra because the sides, the lateral sides, is really one smooth curved surface. It's not a polygon with straight lines. Okay, now we have height, which is going to be perpendicular, that's the altitude. We have r, which is the radius of the circular base, and then again we have the script letter L, which is your slant height. Here's what the net would look like. If we unfold this thing, the base is going to be circular, and if we undo these two edges that were previous together and lay it flat, it would kind of look like a red Pac-Man, which is just a portion of the area of a circle. Okay, so that would be what the net of a cone looks like. All right, let's look at an example. We want to find the surface area of the following cone. So we need to know what the formula is, okay, because this one is not as intuitive as some of the others. Excuse me, the lateral surface area, L, we're still calling it L, of a cone is given by pi times L, the slant height, times r, the radius of the base. That's a pretty important formula. It'll be on the chart. The total surface area is the lateral, pi LR, and we just add the single base, which is a circle. So remember, the area of a circle is pi r squared. Now this is a very, very good problem because our information is not just handed to us on a silver platter. We're going to have to kind of squeeze our own lemonade for this one. All right, what am I given? I'm given that the perimeter of the base, which we call the circumference since it's a circle, is 24.6, and I'm given that the height is 5, and I don't really have the slant height. So for the lateral surface area, I need to know pi, which is pi. It's 3.14. I need to know L, and I need to know R. Neither one I know. So let's go ahead and find those two. The easier one to find is going to be the radius, and it's needed in both the calculations for surface area. So remember that the formula for the circumference of a circle is 2 times pi times r. Well, if we know that to be 24.6, we can actually solve for r by dividing the whole thing by the quantity 2 pi. Just be careful when you do this on the calculator. You're going to have to divide by, and since you're dividing by quantity, you have to put the 2 pi in parentheses. Otherwise, you're going to be dividing by 2 and multiplying by pi. And if you do that, you get 3.915. Now, in this case, I'm not going to use the exact answer because it's not going to be as pretty. So I'm just going to take 3 decimals and call that my radius. Now I need to find L. Well, if this right here is 3.915, this forms a right triangle. So L is the hypotenuse of this green right triangle. So I can say that 5 squared, which is the height, plus 3.915 squared equals the slant height squared. And solving for L by taking the square root, I get approximately 6.350. Okay, so now that I have the 2 pieces of the puzzle that I need for my equation in hand, we can go ahead and do that. Let's go ahead and find the lateral first, even though it doesn't ask for it. And we'll do it as a 2-step process. We'll add that to the area of the base. So the lateral surface area is pi times L times R. I like to rewrite it. Pi, L is 6.350 times R, which is 3.915. And again, the calculator will help you with this. It's going to come out to be approximately 78.101 inches, or I'm sorry, feet feet squared. We have feet as units. Now, for the total surface area, it's going to be that number, the lateral, 78.101 square feet, plus 1 of the base, because there is only one, it's a circle, which was pi times my radius, which I found to be 3.915 squared. And again, with the help of a calculator, got to love those calculators, especially the ones that have batteries in them that work. Those are the really nice kind. We add those two together and we get 126.253 square feet. And that answers the question. That is the total surface area. All right, believe it or not, it is time for the part of the show we call the Say What? That was a weak one today. My voice is not really in top shape. All right, we're going to be talking about pyramids. Now, you've probably studied Egypt, and you know that there they have some amazing, amazing pyramids. We're going to be talking about the Great Pyramid of Khufu. So it is in Giza, Egypt. It's 756 feet long on each side at the base, which is the square base, and it's 481 feet high. Now, that's amazing that they were able to calculate that because it's not a directly measurable quantity. We can find it using geometry. That's pretty tall, though. It was actually the tallest man-made structure before the Eiffel Tower was built, which kind of went a little bit taller than that. Okay, so pretty amazing. It's composed of 2 million blocks of stone, each weighing more than 2 tons each. So each of those is about the size of a small truck. Now the maximum error, this is remarkable, the maximum error between the side lengths is less than 1/10 of 1%. And remember, they did that with rope stretching. They didn't have rulers or anything. So that's a remarkable feat for such a large structure. The base covers more than 13 acres. 13 acres. The sloping angle, the steepness of this pyramid is about 51.5 degrees. Each side is oriented with the compass points of north, south, east, and west. That's pretty cool. They didn't just build this thing haphazardly. Each cross-section of the pyramid, which is parallel to the base, happens to be a square, which looks like this. So there's a lot of neat geometry in these pyramids. This is the only remaining, the only standing, or the only thing that's still around that was one of the 7 ancient wonders of the world. It's still around, and again, it was built for Pharaoh Khufu. These pharaohs were into building monuments so that they would kind of have immortality, and Khufu certainly spared no measure in building his. Now, there was a Greek historian, Herodotus, who was also a mathematician, and he calculated. Let me show you what he did. He determined that Khufu's pyramid, that the square of the height equals the area of each triangular face. He kind of, with the crude mathematics of the day, they didn't have the formula chart like you have. He determined that the height squared equals the area of each triangular face. And we don't have time to do all the calculations, but I can tell you that he wasn't spot on, but he was remarkably close for the technology or what was known for the day. Remember, the height was 481 squared, which just calculating that by itself back in the day was pretty impressive because it's not a directly measurable quantity. That comes out to be 231,361. Now, the calculations to find the area of the triangular face requires a little bit of work, like the last example. So I'll go ahead and tell you that it's 23,1244. This is the area of the face, which is the triangle. They're not directly equal, but look how close they are. These are huge numbers. This is 231,244 square feet. All right, huge numbers. If you calculate the percent error here, you'll see that he was only off by 0.05%. That's about 1/20th of 1%. Again, just remarkable for the day. The ancient Egyptians are a fascinating civilization. I read about them as often as I can. It's just amazing what they were able to accomplish back then and what still remains standing today. Isn't that cool? You got to love the ancient Egyptians. They were way ahead of their time. If we hadn't lost a lot of their technology, or really if we knew exactly what they were doing back then, we might be so much further today. Who knows? Kind of thought-provoking, though. That's all the time we have for today. Until next time, I'm Kevin Corpy, and I will catch you on the flip side.